Hello all and welcome back. It's my pleasure to now kick off the third panel, and I'd like to introduce Craig McLean, the Assistant Administrator for Oceanic and Atmospheric Research at NOAA, who will be the moderator for today's Meet the NOAA Experts panel. Today's panel will provide listeners the opportunity to get a deeper understanding of the perspectives of NOAA scientists and experts in different areas related to climate change. And like all the other panels, you will have the opportunity to really ask questions and get to know what the experts are doing well. Before I turn it over to, I'm going to turn it over to Craig for him to introduce some of his colleagues and highlight some of the cutting edge research that is going on at NOAA. Craig, the floor is yours.
Thank you very much, Rocky, and thanks to all our friends who have joined here from many different components of what we would largely describe as our constituency. We are here to serve the public, and NOAA has a rather proud history of doing that. I do want to start with just a brief opening remark and to let you contemplate where NOAA sits in this particular service role inside of the United States government. Back in 1970, NOAA was founded. I was still in high school when that happened. And NOAA had the specific instruction to do certain and many things, and among them was to study the ocean and atmospheric interaction. After the Second World War and the technologies that were produced there to measure aspects of the atmosphere and the ocean, science understood that there was a relationship there, but had not yet quantified that relationship. So for the next 50 years, NOAA has worked at that and produced what we know today as the answer to that question is what the relationship is between the ocean and the atmosphere. And it is what we call climate science today. We didn't set out to define climate science, but we built the observing system in the atmosphere for greenhouse gases, the satellites that observe Earth from space, and the surface craft, ships, and undersea gliders and detecting devices that measure ocean components. So we established the measurement networks. We defined the atmospheric greenhouse gas content for the world every day, every year. And we've been doing that since 1957 after Ralph Keeling from Scripps started the Keeling Observatory in Mauna Loa. We now have many stations around the world doing that. We have the scientists that analyze those measurements. You have met some and you will meet a few more. Then we also have the modelers, and we heard earlier today, with much pride, how Suki Manabe has been awarded the Nobel Prize for his work as generating, among other things, the first physical model of climate for Earth. So Suki developed the first climate model. Today, NOAA is proud to be labeled by our international colleagues as having one of the best performing climate models that comes out of that very same laboratory that Suki hails from, the General Physical Fluid Dynamics Lab in Princeton. As you have heard from other folks, that Tom Knudsen and also Sarah Kapnick, who came from that same lab as well. So we're proud of the expertise that we have, but we're even more proud of the ability that we have to convey to people like our colleagues and the experts in the insurance, reinsurance, bond, and finance community, what information is reliable and what information extends beyond. As Kelly had offered in one of her examples, there are people who will tell you anything and everything extrapolated from data. Some of it might even be right. And we feel that one of our jobs, one of our responsibilities, is to make sure that there's a competent and cogent understanding of what is the breadth, depth, and capability of the information that we have available to provide to you. So we've been performing the climate mission even before it was called that for 50 years. We're proud of the experts, the systems, and the enterprise that we have gathered in order to be communicating that and conveying it freely to the public. We have a dynamite panel for you here today to pick up on that theme and talk about a little what was rooted in panels 1 and 2, but to let you know what else is available. We've been very responsive in our planning with our good colleagues at Liberty Mutual to make sure that those subjects that are really germane to the insurance and reinsurance sector are brought about here. So without further ado, I'm going to introduce you in sequence, and we'll hear from each in sequence and then roll to the Q's and A's. First is Co Barrett, and Co is our NOAA Senior Advisor for Climate. And Co has been with us for a number of years. She is most notably recognized for her fantastic work in the IPCC, the Intergovernmental Panel on Climate Change, where she serves as one of the 3 co-chairs. Co was very instrumental in producing the Ocean and Cryosphere report, and most recently, Working Group 1, the report on the physical science basis of climate, and Co still is making media interviews and the like in order to explain the complexities, but also the plain understanding of that report. So Co, welcome, our Senior Advisor in NOAA for Climate. Next then, we'll hear from Harold Brooks. And Harold is a senior scientist from our National Severe Storms Laboratory. Harold is an expert in looking at tornadic activity and the storm incidences that come from or drive to them. Next, then, we have Dave DeWitt, who is from our NOAA National Weather Service, and Dave is the director of the Climate Prediction Center. And Dave's center deals with basically time zero out to about 2 years. That's a really key period of time for the discussion we have here with insurers and the like. And then we have Jennifer Mahoney, who is the director of our Global Systems Laboratory, located in Boulder, Colorado. And Jennifer will be talking, among other subjects, but about fire weather, which as we have heard in the earlier panels, is still something that is plaguing us and will likely continue to at perhaps an even greater level of impact than we might see today. So what I'm going to ask each panelist to do is offer some brief introductory remarks about the foundation of your role inside of the services and the science and the information that NOAA provides. And then we're going to follow up with some questions that I'll ask. And I do look forward to the questions that may come in from our attendees that are out in the video world. So, Co, let's start with you if we can. The floor is yours.
Thank you, Craig. I think we have some slides to pull up. Well, they're coming up. Great. So, yeah, hey, everybody. As Craig mentioned, I am a senior advisor for climate here at NOAA, but I also hold the kind of dual role of being vice chair of the IPCC. So I'm going to talk a little bit about the science in the recent report and then shift over to some NOAA parts of the science that I also get a chance to work on. But let me first just say I have really enjoyed hearing the perspectives shared this afternoon and look forward to diving into these issues with you and figuring out how we can make progress together. It's just been such a learning experience to hear from practitioners in the finance and the insurance space about how we can make science useful. So next slide, please. So by now, many of you have heard about the report that the IPCC released last August. It was, as Craig said, the report on the physical science of climate change. And as you all know, planning and problem solving basically begins with understanding. And I think this report provides a great foundation for conversation and the planning and problem solving that we all engage in. So I'll just take a few minutes to review some of the key areas where science advanced in this report and underscore the urgent need for this conversation, which kind of builds on science. So to start with, this report incorporates the latest science to provide more precise climate change data. Advances in science include better historical data, improved climate models, as we've heard this morning, new ways to combine multiple types of evidence. And it tells us unequivocally that human activities have warmed the planet and have already caused widespread, rapid, and intensifying changes in the atmosphere, ocean, and land. And climate change is producing different changes in different regions, which will only increase with further warming. For example, as others have said in the earlier session, climate change is intensifying the water cycle, which results in both more intense rainfall and flooding, but also more intense drought in places. And coastal areas will continue to experience sea level rise throughout this century. And in cities, heating will be amplified, as will flooding from heavy precipitation. We are all experiencing these this summer in places around the world. As the climate continues to change, the world will experience more frequent and extreme events, and many of these events can now be more definitively attributed to human activity. And this report better anticipates the timeline of when the climate system could react to different actions, such as emissions reductions. It finds that without rapid and steep reductions in emissions, limiting warming to 1.5 degrees C above pre-industrial levels will be out of reach. What is the significance of this temperature level, 1.5 degrees C? Well, many countries are targeting this as a goal by which to measure adequate climate action. And the report found that if we fail to reduce emissions sufficiently, we will surpass not just 1.5 degrees C, but even 2 degrees C of warming by the end of the century. This timeline conversation bears out the observation that Mark Osler made in the panel earlier. It's no longer should we act, it is how will we act soon enough to forestall the most dire impacts. And I feel the shift myself as a person who's been working on climate for almost 2 decades. As a scientist and as a former climate negotiator, it is a wake-up call to talk about passing certain thresholds in the next 10, 20, or 50 years. It's no longer about invisible gases causing climate change in the distant future. It's about tangible impacts we're starting to feel now and are sure to feel acutely in our children's lifetimes. And so I've been finding in my interviews and discussions on the report, this is a finding that comes up most often. It's clear that the tangible near-term nature of the projected changes are waking people up. There's so much more to highlight in the 1,000 pages of the report, but maybe I'll just finish the slide by talking about the greater focus on regional information. About 40% of this report is focused on regional changes and regional impacts likely to be driven by climate. And this includes, for the first time, an online interactive atlas that contains the data used in this report. Anyone with an internet connection can use this atlas to perform spatial and temporal analysis at the regional level. Now, this regional information isn't granular enough to guide many of the decisions we've been talking about here today, but it is useful to identify trends, such as drier and hotter in the west and hotter and wetter in the east. But for many regions of the world, this information is the most useful information available to them in their underserved regions, where IPCC is their most trusted source for large-scale climate information. Next slide, please. In the US, we're fortunate to have actionable information, including from NOAA, the trusted authoritative source for scientific information for this nation. And as Craig said, for more than 50 years, predicting and understanding Earth's climate system. But what I love about working at NOAA is we don't just produce information and throw it over the transom. We have boots on the ground activities in every region of the country and work with communities across the nation to ensure that decision makers at every level have access to the information they need to adapt to the impacts of climate change. Still, I think it's fair to say the demand for climate information and services is not currently being met. We see crucial gaps in coverage. There are more than 30,000 communities across the US making climate relevant decisions every day. And of course, they need large scale trend information or models for the future, but they also need tailored information for their particular circumstances to their priorities. And we see significant service equity gaps in low income and minority communities who are often living in the most exposed and hazardous areas and have the fewest resources to get the information they need to plan and respond. The earlier panel, I think, had a really full conversation on this, but it is worth repeating. This needs specific funding, specific programs to address the unique needs of underserved communities. We have programs on the ground. Some, like our regional integrated science and assessment program, have been on the ground working for decades. But the need is so great. I feel like we need an army of trained experts working with trusted local leaders to employ solutions. And I'm that I get a chance to do some of that in my Craig, I'll turn it back to you.
Co, thank you very much. Yeah, I appreciate your introduction. That gives us a good scale, a good scope, and a high level. Let's take a dive down now a little bit lower, and we're going to go on to Dave DeWitt, and we're going to ask Dave to bring up his discussion points about the work that he does at the Climate Prediction Center of the NOAA National Weather Service. Dave, the floor is yours. Thank you.
Thanks, Craig. So I'm Dave DeWitt. I'm the director of the Climate Prediction Center, or CPC, within the National Weather Service of NOAA, as Craig has mentioned. So CPC produces what we would call short-term climate, or now the word we like to use is subseasonal to seasonal, or S2S, prediction, monitoring, and diagnostic products. Our products cover timescales from week 2 or day 8 out to 13 months. Craig is right. Under the weather bill, we're mandated to go out to 24 months. Currently, there are no products longer than 13 months, largely because it's presently a research issue. We really need to explore predictability on those timescales. So forecasts on this time scale have a lot of uncertainty due to the physical constraints in the system, and hence they're inherently probabilistic. Could you go to the next slide? Sorry. Thanks, yeah. And generally speaking, the longer the forecast lead in this type of forecast, the lower the skill and the more uncertain the prediction. So this figure nicely demonstrates these attributes of short-term climate forecasts. The width of the cone shows the degree of forecast uncertainty, and the x-axis shows the time horizon. So you can see that the longer timescale predictions on the left side of the figure are associated with the widest part of the cone, i.e. they have the most uncertainty. Generally speaking, they also have the lowest skill. So many stakeholders can't use a seasonal prediction due to the relatively high uncertainty and the relatively low skill, but they could actually use a shorter time range product that has less uncertainty and higher skill. And a great example of this is actually a collaborative project that occurred between the Army Corps of Engineers, the Bureau of Reclamation, one of our labs in OAR, the Physical Sciences Lab, and Scripps Institute of Oceanography, as well as other partners, where they manage reservoirs using week 1 forecast information that is updated on a weekly basis. This is called the Forecast Informed Reservoir Operations, or the FIRO project. So among stakeholders, water reservoir managers are among the most conservative, given the importance of keeping water for future needs. And the fact that both the Army Corps and the Bureau of Reclamation have partnered with NOAA and Scripps in order to produce these forecasts that they're actually using to manage a few reservoirs is really groundbreaking in terms of what we're doing scientifically, and shows the potential of these types of tools. If we can go to the next slide. So some key points to remember. Forecast skill on these timescales varies by location, field, and lead. As mentioned earlier, forecast on these timescales will always be probabilistic. If someone says they can give you a deterministic seasonal forecast, you should run far and run quick. And stakeholders routinely use these prediction products to inform their decisions. So as to the general question of whether or not the insurance industry could use current subseasonal to seasonal predictions, the answer is it depends. It depends on a number of factors, and the only way to see if it makes economic sense is to perform due diligence by crunching some numbers for your specific context. Second issue I'd like to address briefly is, so what could we do to improve the predictive skill on all these timescales, and especially on the longer timescale? The answer to the question is actually pretty simple, but realizing the answer is extremely difficult. The answer is to improve our representation of key physical processes so that we can model them with enhanced fidelity and reduce model systematic errors. The major systematic errors that occur in the coupled atmosphere-ocean models, great science achievements today. Tremendous recognition for Dr. Manabe as the constructor of the first climate model, Nobel Prize in Physics. Fantastic, but the models have challenges, and we need to address those challenges in order to make them more useful to stakeholders such as yourself. Thanks, I'm done.
Dave, thanks very much. I just want to touch on a point that you made there, and we're going to get back to it, and I'll let you prepare how you might want to respond to this. We can't foresee in a deterministic way, just as Kelly Heride was mentioning that someone was trying to convince her that you could forecast the size of the hail that's going to hit the southern tip of Manhattan 5 years from now, or some similar example that was offered with a bit of jest. But as we have been able to forecast that, as Co said, the wet areas are going to get wetter, the dry areas are going to get drier, and when you do get hit, you're going to have a deluge, the likes of which you may not have seen before. And I think there's a relational value there to the bond assessment of the security of a community. If I have insufficient storm sewers in my infrastructure now, and with an infrastructure conversation going on nationally, how might we restore that? So we're going to get back to that, Dave, but you really pulled something out here I think is worth discussing a little bit further. All right, next up, we're going to invite Jennifer Mahoney, who's the director of our Global Systems Laboratory out in Boulder, Colorado. And Jennifer, among many subjects that she's working on, has emerged to be a very leading voice in our discussion at the interagency level and with the Congress in explaining the complexity of the research necessary in order to foresee, forecast, and give outlooks on fire and fire weather. Jennifer, the floor is yours. Thank you.
Thank you, Craig. As Craig mentioned, I am Jennifer Mahoney, and today I want to focus kind of my perspective on wildland fire observations, research, and some of the services that we provide. So I'll give you a little background. If we could go to the next slide, please. So this is just a graphic really illustrating NOAA's science and services throughout the phases of the fire life cycle. So from the pre-ignition to detection, forecasting, post-fire process, and then monitoring, NOAA has a way of supporting each of those phases as we move through that life cycle. One of the things I want to focus specifically on is the models that are developed out of my laboratory, the Global Systems Laboratory, and really looking at how we integrate satellite information into those models that allow us to improve our weather forecasts, along with providing smoke and aerosol forecasts for the first time that you can see here for the country. And I want to go to the next slide, please, and focus in a little bit more on smoke forecasting. We could get that loop moving, start that loop, that would be great. So this is the high resolution rapid refresh model. It was delivered to operations last year, and this is the smoke product from that model. And you can see some fires that are really prevalent here in California and Oregon and Washington, all along the Pacific area up here in this area, Montana, Idaho, and the smoke that is generated from those fires. This very intense red area are the most dense smoke that you see, and those particulates get carried along with the atmosphere across the entire country. So this is a graphic that occurred in September, and you can see how the smoke has just moved across the entire country. And that's really an indicator of health and air quality issues along with the smoke. A lot of the laboratories within OAR, one specific laboratory, the Chemical Science Laboratory, has done some specific studies to understand the particulates within the fire plume. And so we use that information, if we could go to the next slide, please, to integrate those specific particles into our global forecast. This is another model that was also delivered last year. If we could start the loop, that would be great. Thank you so much. Where we have integrated aerosols into our global model. And you can see similarly, this is a July case this year of the fires along the West Coast in the US, but how those plumes get distributed really around the entire globe. We can also pick up aerosols over in Europe and Asia, and how those get transformed and moved around as well. We're even able to pick up Sahara dust and watch the dust across Africa travel into the US. We had some big dust storms. I don't remember if it was earlier this year or if it was last year. They're kind of all blurring together. But this has been a really amazing model to give us insights and to really understand how these particulates evolve over the globe. There'll be more information I'll talk about later, I'm sure, about how we start to link this information to more of those health and air quality impacts. So that just gives you an overview. With that, I will turn it back over to Craig.
Jennifer, thank you. That's a nice distillation of some of the work that's coming from your laboratory and others in the overall community. I do want to point out for any of our academic colleagues that are listening in, about 50% of the work that we perform in the NOAA research community is performed by academic scientists who work side by side, literally shoulder to shoulder in our laboratories in these NOAA laboratories. So I want to thank our academic colleagues for their many contributions to the work that we have to show here. But I think a major point to take away from Jennifer's presentation is that all of this science is global. And while we might have started with local problems, if we don't understand the global component, we're going to miss the ability to give the best possible forecast outlooks or projections in a local sense. So it is a global series of sciences that we're dealing with. Well, now let's look at what global impacts very locally. And when it does focus locally, it can be absolutely disastrous and devastating. And the work of Harold Brooks, as our senior scientist from the National Severe Storms Laboratory in Norman, Oklahoma, has a very close look at the tornadic activity and is doing marvelous work in helping us to reduce dramatically the warning time to extend the warming time warning time that we have dramatically for citizens to be able to respond to the onset of tornadic activity. Harold, thank you very much for your patience. The floor is yours.
Thank you, Craig. And if we could go on to the next slide, we'll get started. I thought I'd just talk just a little bit about what we do at NSSL. We work on the observation, prediction, and impacts of tornado, hail, thunderstorm winds, and flash flooding. And in particular, we do things like we have experimental forecast situations, and we actually bring in potential forecast users to see how they would use new products, how they can help us design those new products. We believe in co-producing the knowledge with people who will be users of those forecasts, and that's a lot of what we do with our mission. Just really briefly, what we think we understand about climate change and severe storms. We believe that the favorable conditions for severe storms will become more frequent as we go along in the next century. We really don't have much of an understanding about intensity. There's not a clear picture as to whether, say, hailstorms will get to be larger hail, or if tornadic intensity will increase. We have not, or decrease. We have not actually seen anything about that in the past. In terms of occurrence, we've seen that variability has increased, particularly for tornadoes. That's probably our best data set for severe thunderstorms, and that will continue to increase in the future. And I'll show you one example of that in just a minute. What I think has been our recent and our future things where we actually can really use some more brain power helping us out with these things. We're improving in our remotely sensed observations of events and the ways we can see things. Probably our biggest success on that has been with hail, estimating the size of hail falling out of storms from radar. And one of the issues we deal with all of our severe thunderstorm observations is you don't really have a regular observation network that says yes or no, something has occurred. We depend upon an observer being there and frequently depend on damage actually occurring. But we've developed a technique that allows us to estimate the hail size at any time in the country. We actually have about a 20-year record of that allows us now to, there are still errors associated with it, but at least it's sensed consistently over space and time, unlike a lot of our other things. And I think one of the really exciting things that we're starting now that will help us on many timescales is essentially you can think of ways to create weather maps of the entire 3 dimensions of the atmosphere all the time that allow us to estimate where the environmental conditions say that storms are likely to be occurring. And we can use these. We actually have now, back with one of our sister laboratories within OAR, we have this back into the mid-19th century, and it allows us to make pretty good estimates of where we believe tornadic storms and hail should have occurred in the past. And we can now start to use that, we believe, in forecasts out for periods out for 2 weeks, that early part of the subseasonal scale, out actually onto the climate scale to be able to detect periods. Say, if you all remember the latter part of April 2011, which had one of the biggest days for tornadoes in U.S. history, but also was an extended period of a couple of weeks of extremely high activity. We now are on the cusp of being able to estimate how often both those individually really big days have actually occurred in the past and how long those extended periods have occurred. And we believe we will be able to develop techniques that we can apply that to future conditions from climate models to be able to estimate how often those things will occur. And critically, this goes along with the variability in that even though the average conditions may have not changed much or may have changed only a little bit and will change a little bit in the future, if variability increases, that certainly has a big impact on the volatility of risk associated with things. And if we can go on to the next slide, I'll show you one example of how the variability is increased. This is now this is a chart that shows over since the mid 1950s, the number of days per year with at least one tornado that causes damage in the United States, somewhere in the United States. In the top panel in the bluish colors, in the mid 1970s, there were approximately 150 days per year in which there was at least one damaging tornado on a day somewhere in the United States. That number has decreased down to about 100 days. So that's a relatively large change. But at the same time, the number of days with at least 30 damaging tornadoes, so what we might consider to be a really big day, has increased from roughly 1 day every other year to now up to 2.5 to 3 days per year. And it's important to note that the overall average number of tornadoes during this time period, the number of tornadoes that cause damage, has stayed constant at about 500. There's basically no trend in it. So we're seeing fewer days with any tornadoes, but a lot more big days with tornadoes. And that has to have some kind of an impact on the risks that we actually see. So there's an example of how, despite the average conditions over a decade not changing much, the way that the tornadoes have been distributed have changed dramatically over the last half century. And that's what I have to get us started, and we'll go on to the more discussion.
Thank you, Harold, very much. I think what that leads us then to, and perhaps we'll follow up with questions for you on this, is are there telltales here that we could be looking at to see whether there's an attribution element here for that redistribution in the frequency and the concentration of, and I think sometimes people use the word clusters of that tornadic activity. Well, let me take one step back here. We started with CO at a very high level, really talking about climate and the impacts and the development of climate science, its understanding, and the like. And between Jennifer and Harold's discussions about, as I say, among other subjects that these laboratories deal with, we focused in on fire weather and on tornadic activity. Those laboratories then developed products through measurements, observations, models, scientists analyzing all of the above, and delivering a product that is then put in the hands of the people like Dave DeWitt's Climate Prediction Center and other aspects of our service delivery end, which is to deal with the public directly in either a weather forecast from Dave's center or some of the climate engagements that we have through our NIDIS program, our Sea Grant program. Hopefully these are familiar to our colleagues who are part of the finance and the insurance community, because these folks do work rather aggressively to facilitate cogent understanding and availability of this information. So we talked about a number of elements where the threshold of reliability of this information, because of the certainty that we have in this information, might be found. So let me do a lap around the panel real quick with a pretty simple question, but let you just unload a little bit more. Where are we now on the predictive skill of the general subjects that you have referenced so far? And where do you see that next epical advance to be giving the public, whether it's the insurance world or the citizen, and both are involved here, greater levels of certainty? What would that next advancement level be? So, could we start with you in the general sense, and we'll work our way down to greater specificity?
Yeah, well, I think I touched on it a little bit in my opening remarks. I feel like, an area that we have advanced significantly in recent years, at least in this last cycle of assessment, has to do with our ability to reliably attribute human influence on climate. And, I think we see that that kind of attribution really begins with good observations. So, for instance, the extremeness of an event, if you will, is typically measured against historical experience. We don't know that we'll see that in the future, but that's one way we can kind of say, are things getting worse? And that initial part of the assessment hinges on data quality and the length of observations. And I think at NOAA, we've done a really great job making advances in that. We've standardized the way that we characterize observations. We've got climate data records that are all kind of designed to meet certain parameters. And we've done reanalysis of certain aspects of the climate system going all the way back to the middle 1800s. But the next step of attribution is getting at the root cause, and especially for the conversation we're having today, is what's due to global warming. And I think we're making progress on that. It's hard because the rarity of extremes limits how much can be said about global warming effects on, say, a single event. But we are making advances because we can now kind of take these individual cases and do a parallel modeling experiment that kind of helps us to determine whether or not this is something that we would see with climate change. And I think that's an area where we are seeing progress, and there's so much interest in this, probably from the perspective of insurance. There's potential liability issues, but there's still a ways to go on that with regard to specific events and specific decisions.
Oh, Craig, I think you're on mute.
Thank you, Dave. That was a darn good point I was making too. I was impressed with myself. So, yeah, Co, from your comment, it seems that while that uncertainty may remain, we still have an awareness of what the extent of the harm or the range of the harm might be. I may not know exactly what day it is going to befall me, but I know that my risk is enhanced based on what we're able to measure these days. And I think that hopefully can be part of the calculus in the types of risk calculations that the insurance world is making. And certainly our scientists throughout the agency have been and will continue to be available to be providing that kind of guidance, and where the thresholds of acceptable level of understanding might be, or where somebody might be proffering something that is beyond the reasonable expectation of what the data and the models can be predicting. I think panel one did a very good job of describing that. Dave, let's go from the macro down to the real tactical and the pointed level and see where is your threshold of predictability right now, and where is your comfort level in being able to provide obviously the advice that you give to citizens every day, but where do you see those thresholds? Where's the next break coming from?
Yeah, let me circle back to a question you had asked at the end of my short opening. And so everything that I'm talking about is, again, in reference to this week 2 or day 8 out to 1 year. The question you had asked, which is a great question, really goes more into the projection timescale, the climate change timescale, the significantly longer, let's call it decadal, centennial, where I think the models are capable of giving us good first order answers on a relatively coarse spatial scale of the statistics of the variability. So for decision makers who can use the statistics of the variability, is it going to potentially have more flooding, right, or higher rain intensities? That is certainly something that I think GFDL may have already worked with people in the finance and insurance industries, and that's a different problem than I've spoken to. I think for a lot of the problems that we deal with on our time scale, a lot of it is on the shorter than 1 month time scale. That is where you get a skill level that the user's risk tolerance aligns well with the skill profile of the particular products. Now, everybody's different, right? Military planner, they'll usually take 50.1 to 49.9, and they can use that because they're dealing with a lot of different uncertainties. Water manager in the Western United States would like a 90% probability, which if you're going for that means that you're going to a much shorter time scale. So it really is very stakeholder dependent, it's decision dependent, and it's field dependent.
How do you see that evolving, Dave, so that the public can understand that level of risk? What's your feedback as you and your forecasters engage with the public?
Yeah, so it's a good question, Craig. Mostly on the Weather Service, we're really more engaging the deep relationship core partners who have some more quantitative knowledge. I do think forecast uncertainty is an area of science that we need to do a lot more work on, and I think everyone recognizes that. We're very fortunate to have an initiative in the 2022 budget that if Congress appropriates the funds would look explicitly at that, at providing user-informed uncertainty estimates that are meaningful. And again, I would say that it's different for every stakeholder, and it's different for each sectoral decision.
I would suggest then, Dave, that that's probably a partnership undertaking that we could be looking at academia, government, and the industry, because the more the citizen knows and understands what risks they may be facing, the more they're content to modify their own behavior to anticipate that risk. But then also that would potentially lower the cost of damage if we're building to more resilient structures and standards and such, as Mark Osler in the second panel we're talking about. So there's a lot here that intersects quite tightly. All right, let me jump for a minute now and go back to fire weather and ask Jen if she can give us a little bit of a discussion. And this was a question that came from our insurance colleagues, that fire weather, we understand it. There's an ignition, there's a wind, it drives. But how do we know when an area is going to be ripe for fire? We can't necessarily forecast the ignition point. But Jen, could you explain to us a little bit more where the science is leading us to know where are the risk areas and how do we know that they're risk areas? What goes into making that determination?
Thanks, Craig. I think to get into that a little bit, I wanted to go back to understanding two things. One, being able to observe more than we have ever been able to do before using our satellite data. The satellite data that is really coming to fruition is providing the information for not only fires igniting, but giving us an indication of the vegetation, the state of the vegetation, how dry it is, where is it dry, those sorts of things. As we know, there are really three basic ingredients, and that is the state of the vegetation and kind of how dry it is, the trees that are dead, the grasses that are dead, those sorts of things, which really come from, prolonged climate impacts, very hot, dry, windy weather, sustained lack of precipitation. So, kind of taking off on what Dave was saying with the probabilities, looking at long-term probabilities of temperature ranges. Is this going to be a potential high temperature, above average temperature area, and then overlay that with, are we getting low probabilities of precipitation to give us an indication of what a season might look like in particular areas. And then actually looking at the weather changes as we start getting into a particular season. Are we having hot, dry, windy weather? As we saw in Alberta and the Pacific Northwest just this year with the extreme temperatures that we received, over 100 degrees, 120 for a sustained week period in Alberta. Just those really hot, dry temperatures can dry out a area very quickly, making it prone to fires. And then you have an ignition of some sort, and you can set the whole area on fire much more quickly than anticipated because of those long, hot, dry, windy areas. So I hope that answered a little bit of your question. Did you have others?
Yeah, let me probe a little bit deeper on that then, Jennifer. Thank you for that answer. Now, we're familiar with the rather well-known and established phenomena like the Santa Ana winds in California. In this and in most previous fire seasons of very proximate years past, we've seen wind events that are driving fires that may have been previously understood as atypical. Can you offer some remark about how this whole complex system is arriving, where we even have fire-driven winds, not just the normal seasonal, let's say, Santa Ana wind of California, but there are things that are happening now phenomenologically that are very atypical from what the past has recorded, and is we know that past is not the prologue, but where are we headed here, and what are you seeing from the study of fire, its genesis, and the ripe conditions for fire?
Right. So we can have intense heat. So the types of fuels that are drying out now can really encourage an intense heat. If you have an intense heat, you can actually drive your own weather conditions because of the heat with which it's being, driven by the fire. They're called, pyrocumulonimbus clouds, which are really intense heat driven from the fire, engaging and making its own weather conditions where, plumes are going very high, water is condensing, and it's making an environment that actually then increases the winds in that area and moves, the fire more quickly, whatever direction it's headed. It can bring up embers and start new fires. It can have, it can be ignited with, different types of just moving embers around and starting new fires in new directions. So you can actually increase the fire potential because of it feeding on itself, because of the extreme intense heat from which it comes from, and then the types of fuels with which it has to burn in that area. And there's a lot of research trying, to going into understanding these phenomena a little bit more, because it's those sorts of situations which really will impact the firefighters on the ground, because they move so rapidly and so quickly through a particular area. And getting people out of the way in time, notifying people in time, really becomes an issue because of the rapid increase and the way in which those fires move so rapidly.
Thank you, Jennifer. Let's switch back then to tornadic activity, Harold, and let's go back to some of those things that we were touching on in your introductory comments, that you remarked that there would be an increased frequency in the type of weather that would give rise to tornadic activity. And then we also saw the rather clustered phenomenon as opposed to the singular event. Take us down a little bit deeper into your understanding of what's going on here.
Well, I think we have a lot of confidence that the frequency for severe thunderstorms will increase. Tornadoes are a little bit harder to tell. In terms of global scale impacts on them, there are two primary ingredients we look at, essentially one that's related to the temperature and moisture profiles of the atmosphere, and one that's related to the vertical wind profile that storms form in. And one of the things that makes the tornado problem really challenging is that our understanding of, from climate scale influences, is that the thermodynamics, the temperature and moisture profiles will become more favorable, but that the wind profiles will likely become less favorable in the future. And so we have this balancing act that we have to watch out for. And certainly for hail, we're confident that the thermodynamic profile impact will win. For tornadoes, they care a lot more about the wind profile, and so it's not clear what's going to happen with them in the future. And the notion of the clustering it's almost certainly, I mean, my gut feeling is that that's related to this change in potentially a change in the patterns that we see, in the frequency of favorable patterns and how well they're distributed. And there we run into a missing link in how we relate that pattern change to how the planet-wide atmosphere is changing. And that's been really challenging to get it down to the scale that actually tornadoes care about. And that's, I think, one of our big questions going in the future is, can we actually make that complete link in the chain?
Harold, thank you. I'm going to ask Harold, Jen, and David a specific question here, and then Co, I'm going to ask you a more global one about El Nino frequencies. But for Harold, Jen, and David, be thinking, and I'm going to bounce back to you after the Co question here. It takes on average about 8 years at our current level of budgeting in NOAA to take a discovery, technology, improvement, development, et cetera, and to put it into operational use, largely because of finances. I have been quoted as saying, and I'll say it again in this forum, NOAA is about a $12 billion agency trapped in a $5.5 billion budget. If we had supportive partnership-based funding to reduce some of this waiting time, to deliver products to the public quicker, that could be of benefit to the industry that we're talking to here today and the constituencies that they and we represent, what would those low-hanging fruit, highest level of return areas be that you would like to dive into, and that you might be able to say, here's an opportunity for partnership? So Dave, do you want to start first?
Sure, Craig, and absolutely.
I tricked you. I'm sorry. I said I was going to ask Co the question, but we're going to let you guys go first because we're on a roll here. Co, stand by. Thanks.
Yeah, so I would say absolutely. And to go back to the point I made earlier, the models are great, fantastic scientific achievements that have major errors that have existed actually since Suki made the first one. And the reason is that we have physical parameterizations because we cannot explicitly model all of the processes we need to model. And so anything that we could do, any investment that would help us remove these systematic errors and provide better fidelity of those physical processes would help us to improve our forecast skill, especially on the time scales from week 2 out to decadal centennial.
So Dave, is that more people working on the job doing what we have been doing, where we see, for example, postdocs sponsored by insurers, reinsurers, working within our laboratory and science environment, helping on these problems?
Yeah, so certainly having more scientists would be great. I think resourcing our current scientists would also go a long way. I think the high performance computing is a major challenge. Our business is nonlinear partial differential equations. We need a lot of computing to do that in order to get higher resolution models, in order to get better fidelity with these physical processes. You need to increase their complexity. So high performance computing, investment in the NOAA labs, as well as an investment in the academic community would be the place to put that money.
What I'm hearing you say too, Dave, is that academic research is one thing and remarkably beneficial. It's gotten us pretty far down the knowledge curve of where we are. But the focused targeting of specific questions, specific problems that are key to the operational performance of our forecasts and the like are very important to us. I appreciate that. Jen, let's see what you have on your front. And don't feel
Sure.
limited to fire, but because I know your lab does a lot of diverse work.
Right. We can use fire as an example where, we're building these models, weather models that are producing output. What's missing are the products that then interpret that model output and make it usable for different sets of users, whether it's through displays or graphics or products or, that piece of information that takes and interprets all of that model data and really makes it actionable on a user end. And I think it was the first panel, they were talking about disaster models, and particularly disaster models from the insurance company point of view. They have specific questions and needs that will then help them, put together the disaster scenarios to set certain rates. The interface to our weather models and those disaster models is what makes this process work. So joining together to say, what do you need on your disaster side? What questions are you answering? What time scales do you need? What, outcomes are you looking for? And then joining that information together not only achieves a transition, but it brings the communities together to make useful information from our models. And realizing that our weather information, as Dave points out, isn't perfect, but we're getting better at understanding the uncertainties, the errors in our models. We're trying to improve those models by bringing in additional observations, but understanding those connector points really then makes our information usable to that end user.
I think something else for us to focus on as a united community on all sides of this conversation in this workshop might be on those observation networks. I know that we had discussions for, I'm going back to panel 2, but for sea level rise, greater density of observations could be much more telling in terms of even after event consequences. Let's see, Harold, what are your thoughts on that? The low-hanging fruit, where would you like to see some opportunities of assistance if we could manage them?
There are two big areas. One of them is in some sense just people to turn cranks, and that has to do with improving our extending the period of our remotely sensed observations of things like hail. That we've collected the radar data, but we haven't updated the radar estimates of the archive of radar estimates of hail occurrence for a number of years, and we don't yet have the equivalent for non-tornadic thunderstorm winds or even for tornadoes that could allow us then to have a long record of, say, 30 years that are completely independent of the human observing system, that will be consistently collected all over time. And a lot of that is simply just somebody needs to run the code and have the disk space to put it out and maintain it. Because NSSL is not an operational agency, and so we don't necessarily go, well, let's add one more year to the data set. On the other time scale, on the longer time scale, when we look at the pattern analysis and using the patterns, we've got, if you count all of us who think about the problem at the lab, we probably total up to somewhere close to 2 people. That's scattered among a few people. And we have a lot of ideas, but way too much that we want to do for the number of bodies we actually have. And I think it's a real prime opportunity for things like postdocs that could come in and could address serious problems in interesting ways, and to be able to look at the historical record, to be able to apply it to climate models, to be able to do a lot of to build the better statistical models for relationships. And then with that, one of the big successes I think we've had at the lab in terms of how we look at forecasting over the first few days of the forecast period are partnering with television broadcasters and emergency managers to develop experimental products that they would find useful. And then slowly but surely they get into the operational stream. When we look at the subseasonal to seasonal time scale forecasting of tornado and hail, it's not actually even clear what's a useful target forecast. Is it, say, the total number of tornadoes in a season? Is it the number of of days that have any tornadoes, the number of big days? Is it a week that's really big? Or what kind of a forecast product is useful? And the little bit that we do know, unfortunately, our best predictability out, say, for the seasonal forecast out for a few months appears to be in the winter season, where there aren't very many tornadoes. So we can tell you it's above normal, but it's above normal for not for a low period. And then for the summertime, which again is not as interesting in many ways. And our lowest predictability is in the springtime, when most of the major outbreaks occur. And if we love to be able to figure out a way, and this requires some better ideas than we've had so far, about how to advance the predictability at the most important time of the year.
Harold, thank you very much. It seems to me that we've got opportunities here to close some of the gaps. And one of the points that I've heard you make a number of times, and we all discuss this quite frequently, is that NOAA is very centric in all of this. And in some cases, we don't do it alone. USGS and USDA are providing Jennifer and her team with the observations that are needed. Some of the observations that Dave spoke of, we get from many different places, including FAA-based measurements at airports, as well as the National Weather Service themselves. And Harold, I think the same is for the phenomena we're measuring. But could you talk about the engagement and intersection of how NOAA is kind of party central with many other agencies collaborating and cooperating with us in climate and climate relevant science that impacts weather and these types of phenomena?
Yeah, I'd be happy to. So, well, Craig, you're spot on. I mean, NOAA does have, authoritative science to offer for oceans, atmosphere, and land, but so do many other federal agencies. And it's important for us to kind of work together to make sure that our data is interoperable and that we're working together to solve some of these complex problems. It's kind of, there's a number of different whole of government activities that are underway now under this administration, this presidential administration. And a big part of that is bringing all of the federal agencies together to tackle pieces of this problem that each of us have kind of a piece of. I was just a part of a panel last week that was put on by Amazon Web Services that had NASA, Department of the Interior, and myself talking about how we are kind of working together to get our data sets into the cloud so that people can access that data free of charge from all of our agencies to do their own research. And it's clear that the interagency federal effort is important, but what's really important if we really want to solve this complex problem is engaging as many diverse perspectives into the problem-solving space, and that means giving people access to the data. Amazon has a sustainability grant that allows people who don't have their own compute to also do the computing in the cloud. And I think it's an important thing to recognize that we've got so much to share between ourselves, but also with all of society to solve the problem.
Thank you very much for that answer and for that recognition. When we saw that no one entity exists as an island, and we saw the history of where and how NOAA had developed. We saw many other contributory elements coming from other agencies. We went through a period where climate was denied. We went through a period where climate budgets were proposed for reduction. Our own budget was proposed in climate for over 60% reduction. We're now at a point where the wave is coming back up. The crescendo is there, and the public is recognizing this. I think this is a season of opportunity for, let me take the position, and forgive my ignorance, but I'll put myself in the position of the insurers, where you want the public to understand better what their risk exposure is, and then work to mitigate the risk. And I think we have good communication vectors throughout the organization. The National Weather Service has communicators. I mentioned some of the other programs that we have as well. And we're in a position where we're able to be bringing more information to the public for their understanding, whether it's fire readiness or fire risk or exposure to severe weather phenomena between Harold and David's services that we provide. We're in a season of opportunity. What I hope we have accomplished through this panel is creating an awareness with our colleagues who are the other half of this partnership for this workshop, the insurers, reinsurers, finance, et cetera, that we can be breaking out into refined discussions in the groups that we've set up here. carry this further and help any remaining questions that we have get answered by focused work sessions. And we're your government. We're here to help in driving that. And it occurs to me that we have many roads that we can go down on each of the 3 panels that we went on here. But let me close here. We're looking at just about 4:20 now, which is about the time that we're supposed to run out. We probably have time for one more question because our organizers are giving us the mode of forgiveness here. If you could see anything develop in the next 5 years that would help your area of achievement, accomplishment, et cetera, particularly bearing in mind that we're working with the insurers in this discussion, if you could see anything happen, what would it be? And let me start with Dave. It's your wish list. 5 years.
Craig, yeah, I have the one horse. I'm a one horse guy. If we could fix the boundary layer convection interaction, we could do a better job on precipitation forecasts, which would be useful for you from tornadoes to hurricanes to excessive rainfall events like we experienced recently in New York and New Jersey.
So let me probe that, Dave, because some of the folks listening might get it, but might need a little more explanation. The boundary layer, obviously the atmosphere and land interface or ocean interface, we just put a glider along with sail drone right into the heart of a hurricane. That's a first. That happened earlier this past week. But what other types of observations and tools do you think we need?
Yeah, I think we need the really bright people actually sitting out in labs like GSL with Jen, Stan Benjamin, Curtis Alexander, people like Tom Hamill in PSL. And we need to let them go and try to actually work on these really complicated problems that they might not get 100% perfect answer, right? So I like to describe it as we need to embody higher risk, higher reward research that's operationally focused.
Thank you, Dave. That's hard to do on a strangled budget, but there's optimism in what we're seeing now with the current administration reversing the trend we saw previously. Jen, what do you think?
I really think, going back to what Co said, we have to broaden our collaboration and the people we're collaborating with. When I think about moving fire weather forward, bringing in the other agencies and engaging in partnering with understanding what they can contribute, what we can contribute, but bringing the insurance company to that discussion along with those end users gives a whole different perspective of what kind of products need to be generated on what time scales and what they need to look like. So it comes back to, I think, not only sitting and developing our science, which needs to occur, but that has to occur in a context where we bring in users to help us formulate what that science is needing so that we have a place to put it. So that's my message.
And this workshop is a good start at that. Very good, Jen. Thank you. Harold, what do you think?
Coming up with a few 100-year, both past and forward, looking, understanding of how patterns relate to severe weather events in a way that someone on the planet can find useful to use to make decisions with.
All right, so we're getting back to compiling that data that needs to be yet compiled as well, right?
Some of it's compiling data, some of it's also just answering this question of what do we really need to be trying to develop the statistical models that will predict how the patterns relate to something that someone cares about, as opposed to just, it's not just predictable, it has to be useful.
Very good. Co, you have a 1.5 minute answer, which on TV time, that's a long answer. So go ahead, please.
I think I'll just pick up where Jen left off. I think we need an army of climate practitioners. Maybe it's the Climate Conservation Corps, who are trained up to provide resilience information to these thousands of communities across the country who need the information to be able to act on it. And, the research shows that people who come from a community are often a trusted voice in that community. And there's places where federal agencies just cannot be as influential as they need to be. And we need just an army of people who are trusted in their communities to advance the issue and help us to address this existential problem.
Co, thank you. Let me reach back to Louis Uccellini and the National Weather Service with impact-based decision support and providing the information for that, right? All the weather information is not just what's going to happen, but it's what's the significance and what's the probability of it happening, and having the local emergency managers understand that and be able to convey it to the public. That's also analogous to the Sea Grant model, where we work in communities, or in land grant with agricultural extension. So I think there's something there to that. This whole workshop, this panel has been a great success. I want to thank each of you for your joining. I want to also thank Kelly Heride, because Kelly and I started as co-panelists some months ago in an event, and we said, wouldn't it be great to get our two communities together? And thanks to everyone who decided that, yes, let's do. And in particular, in putting this together, I owe my thanks to our Chief of Staff, Jim Jenkins, on the NOAA side for helping to move this forward. And then also, of course, to Rocky and your team. So Rocky, I'm going to turn the floor back to you with my thanks to Co, to Harold, to Jen, and to David. Thank you very much, panel. This has been delightful and informative.
Thank you very much. And thank you so much, Craig, and agree. This has been a fantastic partnership with NOAA, and a lot can happen if both sides just start talking to each other. The last panel, you're left with some very good ideas on how public and private and particularly the insurance companies can work with NOAA and work with other agencies in the government to really get more information and data with the eventual goal of protecting communities. And so hopefully today's discussion has helped us one step closer to making that a reality. So on behalf of our organizers from NOAA and Liberty, I'd like to thank you for taking the time to engage in today's workshop on climate and risk resilience, or resilience risk. I'd like to thank our speakers, moderators, and panelists for sharing their expertise on such a timely and important topic.